When you really think about it, this is incredible. High schoolers and undergraduates are learning calculus. It was only invented in 1687 by Newton. So if you're taking calculus, that's really impressive. Of course, homework is boring as always. I didn't enjoy writing this. But calculus is a very powerful tool, and I want to show you one of its applications right now. Consider this sequence of rotations. At each step, we rotate by 1 radian and we keep going. Eventually, we start to see a pattern. And that is that these points are spread pretty evenly around the circle. And very evenly, as you can see. But what exactly does this mean, and how can we prove it? So we need to think about distributions, right? How are these points distributed? So how many are in this top half of the circle? If you do some counting, you get that exactly 1/2 are in the top half. And similarly, about 1/3 are in this third. So let's make this formal. So the proportion of points in an interval should be its length over the circumference of the circle. And because I don't like fractions, okay, so let's prove this simpler result. Remember, we want to show that given any interval on our circle, we can find a term of the sequence inside this interval. And this could be literally any interval on our circle. It could be this one. And most critically, it can be as small as we'd like. And it's not at all clear that our sequence visits such small slices of the circle. So let's stick with this interval for the purposes of this proof. Now the first thing we're going to do is that we are going to subdivide this circle into equal parts such that the length of each part is smaller than the length of the interval. So that's the important thing about this subdivision. And now let's just take a few points of our sequence. Now eventually what will happen is that 2 points of our sequence will land in the same part of the subdivision. Now here we have 7 parts, so when you get 8 terms, 2 of them will fall in the same part. Now let's just focus on these 2 terms. Now this one is a rotation of 1 radian, and this one is a rotation of 8 radians. So their difference will be a rotation of 7 radians. And the key point is that because these 2 are in the same subdivision, their difference will be within one subdivision of this green point. So this purple dot must lie either here or here. Okay, so now let's ignore everything else and focus on this dot. Now what we're going to do is that we're going to take multiples of this point. So for instance, 14 radians, 7 times 2 is 14, and then 21 radians. Eventually what's going to happen is that you're going to land in this interval, and that's because the distance between 2 points is always less than the length of the interval. So you can't really go from here to here, bypassing this completely. And that's it. So we've shown that our sequence visits every interval on the circle. Okay, so now that we've proven denseness, we are equipped to deal with uniform distribution. So here's the definition. I won't read it again, but it's telling us that the proportion of points in I approaches the length of the interval. You should think of this quantity as the proportion of points in I, because that's essentially what it is. And what this tells us more philosophically or qualitatively is that this just depends on the length. Sure, it equals the length, but that means it just depends on the length, and this is what we'll try to prove. Okay, so we want to show that if we have a circle and 2 intervals on it, then the proportion of points in them is the same. And these can be any 2 intervals as long as they have the same length. They can overlap as well. But for now, let's just fix j to be this interval. And another thing we'll do is that we'll think of I as a shift of the interval j. And arbitrary shifts of j are hard to think about, so let's pick a convenient shift. So we'll think of, so first suppose that I is a shift of the interval j by 1 radian, by which I mean that these 2 points differ by 1 radian. Now here's the nice part. If you have a point of the sequence in the interval j, then the very next one will fall in I because they differ by 1 radian. But this means that a of jn and a of in differ by at most 1, and this makes no difference in the limit. So these two limits, that is the proportions, are the same. Okay, now suppose that I is a shift of j by 2 radians. Now if a point falls in j, then the next point might fall somewhere else, but the one after that must fall in I, because I and j differ by 2 radians. And by the same argument, these proportions will again be equal. And if I is a shift of 3 radians, you know the drill. And in general, if I is a shift of j by a whole number of radians, then the proportions are equal. Okay, so what if I isn't such a shift? Well, then they differ by some angle, but this angle can be approximated very well by some whole number of radians. And why is this? This is because of denseness. It's essentially what that means. And so we can pretend that I is a shift of j by a whole number of radians, and then you wave the wand of calculus. So we've laid all of the groundwork, and now we can prove uniform distribution. But first, take a circle, divide it into equal parts, k equal parts. Here we have divided it into 5 parts. Each of these parts gives us an interval. Now by shift invariance, the proportion of each part is the same, and the proportions of all of these add up to 1, because the proportion of the entire circle is 1. So if you do some algebra, you get that the proportion of each of these is 1/5, which is their length because the circumference is 1. So the proportion of this is 1/5. But now what about the proportion of this combined interval? Well, we have 2 intervals of length 1/5, so the combined proportion is 2/5. And similarly for this, the combined proportion is 3/5. And generalizing this, we get that any interval of length m over k has proportion m over k. But that means we're done, because any length between 0 and 1 can be approximated by such a fraction, so the proportion of any interval is its length. All we have to do is wave the wand of calculus. And that's it. We're done.